Okay, here we go. Buongiorno. Almost good afternoon, actually. I'm Alex. I'm Alex Casalboni. I'm the first Italian on stage today. So if you have any questions in Italian, that works too. I'm a developer advocate or technical evangelist with Amazon Web Services. So today I want to dive a bit deeper into one theme that we haven't touched yet, which is performance and cost. There are a few things, as everything else, as observability and business and everything we have seen so far. Also for cost and performance, these things change a lot when you develop and when you design systems in a serverless fashion. So fundamentals, some optimization best practices, and I'm not saying explicitly cost or performance optimization because in my point of view, they are very related to each other. So we'll look at it in a related way. Then I want to give you an idea of how you can do this kind of optimization in a data-driven way, in an even automated way. And then I want to show you some examples, some patterns, some real-world data and scenarios that you might encounter when you do build and implement your own serverless functions. So some fundamentals. We have already had a few talks about serverless, so I don't want to say again and tell you all again what is serverless about. This is how Werner Vogels, the CTO of Amazon, talks about it. As developers, all we want to focus, all we want to do and care and do all day is implementing, writing code and solving problems and focusing on the business logic. Everything else is overhead. Everything else is something you have to do because you have to. It's not really solving a problem. It's not differentiating you. That's why when Lambda came up, when AWS Lambda came up in 2014, 2015, this idea of function as a service kind of revolutionized this idea that you don't have to maintain, own, purchase, and manage infrastructure, computing infrastructure yourself. And now, 5 years later, so first of all, you can say that you have 5-year experience on serverless in 2020. It's possible. And also, we tend to talk about a spectrum, not just function as a service. Although, for the matter of optimizing compute capacity, optimizing compute performance and cost, today we'll mostly talk about function as a service, which is AWS Lambda on the AWS platform. But remember, it's a range. It's from the virtual machine or even the on-premises world where you have the bare metal instances, for example, all the way to serverless. And there is things and services and solutions in between. It's not all black and white. And most of all, it's not just computing. It's databases, it's data analysis, it's everything else could be kind of put and positions in this spectrum of serverless versus serverless full. That's what a Lambda function looks like. I think the signature is kind of similar for other platforms too. So most of the examples I'm talking about today are AWS focused. I hope you can learn from this presentation even though you're not using AWS, by the way. So usually you have a handler or some sort of actual function. I've met a lot of people that confuse the idea of a Lambda function or serverless function with the idea of a programming language function. Okay, inside your serverless functions, you might have function, classes, whatever data or programming structures you need. In this Python example, I do have a Python function. In a Java example, I would have a Java class. You can use any programming language on AWS Lambda. And then we talk about events. We have talked about events a lot today. Everything that happens in a function as a service world is an event. An HTTP request, a new object on your object storage, a new record in the database. Everything is modeled as an event. That's why your handler usually takes an event and a context as input. A context is metadata about the invocation. Who is calling you? Who are you right now? Where are your logs? How much time you have left before timing out? These kind of things. What actually happens when we talk about performance and cost? So there are a few things that need to happen before the platform itself can run your code. So we need to download it. We need to bootstrap some sort of, we call it micro virtual machine powered by AWS Firecracker. It's not really a container, but it kind of looks and behaves like a container. Yeah. And then we have to bootstrap what we call the runtime. Runtime is everything that you need to run your actual code. So if you choose the Java runtime or the Python runtime or the Ruby runtime, depending on which runtime you choose, we bootstrap it you can actually build your own runtime if it's not supported by default. And then we can finally run your code. And that's the 20 lines of Python, 200 lines of Java, 50 lines of Go, whatever you are providing as your business logic. So we have talked about a cold start concept today already, and there are ways to observe it, there are ways to monitor these kind of things. The cold start is everything that needs to happen before we can actually run your code. Every now and then, every once in a while. If you don't run if you don't invoke your function for, 10 minutes, half an hour, 2 hours, the next time you do it, you will encounter a cold start. Or if we have 1,000 concurrent invocations, because you have a peak right now with 1,000 people calling your services, all those new requests will have to hit a new runtime, and we will bring it up, warm it up, and then it's ready for you. When it comes to optimization, there are a few things that we are constantly optimizing under the hood without you even noticing, because the interface remains the same. And there are a few other things that you are responsible for optimizing. This idea of shared responsibility model applies to security, to cost optimization, to all these kind of things. Why is the runtime also potentially your responsibility? Because you can build your own. If you're using a native built-in runtime, well, that's also our responsibility to keep optimizing it. Mostly your responsibility is your code for security, for optimization, for everything else. A little update. I don't know how many of you used Lambda in the last few years, and there was this kind of broken heart between Lambda and VPC. VPC is the virtual private cloud, your private network inside AWS. If you wanted to deploy your Lambdas inside VPC, you had these very long cold starts because of the way AWS, VPC, these services were integrated together up to tens of seconds. Okay, this is gone. I can tell you today, this is gone. Now, the cold start of a Lambda in a VPC or not in a VPC are the same. So this is gone. The rollout started in September last year, and it concluded in December or November last year. So 2020, no VPC cold start issues anymore. In all regions, you're good. Now that's out of the equation. How can we optimize our functions? I'm focusing on functions specifically. Of course, there are other things you can optimize at the architectural level. And I tend to distinguish two macro categories of optimizations. The ones that are meant to reduce the cold start time, because that's let's say in many systems, that's an issue if you have latency-sensitive applications or customer-facing applications where a cold start may impact the user experience. Imagine a RESTful API. If we have half a second cold start, once in a while, some user will have a bad experience. Okay, you want to minimize that depending on your business needs. Now, there are a few things you can do. The first we always recommend is trying to avoid monolithic functions. Monolithic meaning that, okay, we want to build microservices, but you can still put all your code in one function, right? And that works great, but it doesn't. It's an interesting way to do some lift and shift to serverless, check it out, get some experience with it. But at scale, this is not really an optimal way to run your serverless functions. So first of all, try to do that. Go towards an actual micro or even nano services in some organizations that's even better. The idea that you can also optimize your dependencies is very important. There are some articles by our serverless hero, Jan, that you met this morning. He shows how, for example, if you're using the Node.js SDK and you import only a subsegment, a submodule of that SDK, you can cut off hundreds of milliseconds off your cold start. So that's interesting. There are a lot of numbers and comparison tables about how that might impact your cold start. Another tactic might be to minify and uglify your code. In some languages, it's easier. In others, it's by default. If you're using Node.js, for example, there are 200 million options to do that, Webpack, Browserify, and so on. Another interesting trick, but not really a trick, more like a a tip. If you have a lot of functions in the same file, a lot of handlers in the same file, this might be stupid if you have thought of it already. But I see a lot of developers, they like to have one big file with 10 functions there. And then they put all the initializations code at the top, all the SDK modules, all the parameters fetching from other systems. Now, if you have 10 functions and all their initialization code is up there, it means that initialization, that is one of the main causes of cold starts, is hitting all the time for all those 10 functions. And maybe the individual function is only responsible for half or 1/10 of that cold start. So there are ways, if you either split one function per file, or if you do this lazy initialization, so that you don't really have all the initialization part up there, but you only define objects and then you initialize it in a lazy way down inside the handler. So this is a little tip if you really like to have a lot of handlers per file. In Node and Python and other languages, this is very common. By the way, this is a new functionality that kind of helps you fix the cold start issue. It's a managed way. We announced provision concurrency for Lambda. That means that you can just say, hey, for this function, I need 100, 1,000, 20,000 warm runtimes from now on, and then it will ramp up, and we take care of warming up these runtimes for you. So up to that quota, if you have 1,000, for example, up to 1,000 concurrent executions, you're not seeing, nobody of your customers, of your invocations is seeing any cold start at all. So that's a managed way to fix it. There used to be workarounds, maybe CloudWatch events or other tricks to fix that. But at really large scale, when you have thousands and thousands of events, it's not really something that work great. Imagine you have 10,000. Imagine you are a streaming platform, and you know that at 8 p.m. there is a big soccer match or something, and you will have a lot of requests to your services, and you can predict that. It's a predictable peak, it's not random, it's very predictable. So if you do that, you can prepare for it, you can provision this concurrency, and those 10,000 invocations that just show up at 8 p.m., they will not experience any cold start. So that's a managed way, a new way. We announced it a couple months ago. Let me try to fix this. Then there is another set of best practices that are not really related to cold starts. And in my opinion, this is where actual optimization matters, okay? Because cold starts, at the end of the day, is, I don't know, 1%, 5%, in the very worst case, 10% of your executions, but the largest majority of your invocations, of your serverless functions invocations, they're not cold starts. So if you actually want to minimize cost and optimize the experience, you want to optimize everything else. So here there are many tactics that you can use. For example, if you have a lot of sleep here and there, do start a task and wait for it to complete, you're just paying for idle. You're just doing some orchestration inside your serverless functions, okay? That's not optimal. You can delegate that orchestration to an external service, maybe step functions. And then this idea that you don't have to use Lambda functions to transport a lot of data, like downloading large files from S3, for example. There are more optimized ways to do it. You should use Lambda functions to transform data so that the data comes already as part of the event, for example, or you can use specific feature, for example, for S3, you can use S3 select to extract only exactly what you need from that S3 object instead of downloading the whole thing. If it's 10 megabytes or 2 megabytes, you can only download those 20 kilobytes that you need from the file, running an SQL query on top of the S3 file. And that will reduce drastically the performance of bytes on the network and therefore the cost. That's why I think cost and performance are very related to each other in a serverless world, because if you can run faster, there is a good chance your workload will be cheaper as well. Now, this is not true in every computing platform. The idea that you can discard uninteresting events. So if you are processing images uploaded to an S3 bucket, but you only want to have JPEGs and PNGs, right? That's what you need. So you don't really have to add an if statement in your code saying, I only want PNGs and JPEGs. You can add that filter on the S3 level. So those invalid events are not even hitting your lambdas. And that means you're not paying for those executions, so you're cutting costs. Then you can fine-tune the allocation of the resources. So how much memory, how much power, how much CPU, network, and RAM you are providing to your functions. Now, that's actually only one handler. I kind of call it power. And there are ways to not guesstimate it, to not randomly guess it. And we'll talk about that in a second. Another interesting new feature is Lambda destinations. This is a way to say when this function succeeds or fails, its output will go to another service like SQS, SNS, or even another function. So this can give you a way to do simplified orchestration. You can do dead letter queues to handle failed events. But also, because you're not paying for the network call to put that event into another service, you're not paying for those 20, 30, 50 milliseconds of execution, right? So that's another 30, 50, maybe more milliseconds that you can cut off your Lambda bill. So you still need to have permissions to do that API call, but you don't have to do it. You don't have to write that call, and you don't have to pay for the milliseconds to run that API call. Last thing is retry policies. So it's not really a technique to save money, but keep that in mind, because every time an asynchronous event fails, it will be retried a couple times. So first of all, now you can decide how many times. Could be 2, could be 1, could be 0 if you don't care. So keep in mind those retries are not free. Okay, so that's another cost-related thing to keep in mind. Today I want to focus on one of these best practices, one of these tips that actually does not force you to re-architect the whole thing. Most of these tips, if you look at them now, they force you to change your code, to re-architect the overall architecture, to change something, to change your CloudFormation template, or whatever you're using, you need to change the architecture. There is one thing that doesn't force you to do that, and that's resource allocation. And you can do it in a data-driven way. So I want to dive deep into that today. So disclaimer, I'm going to call memory power from now on. Because when you provide your Lambda functions with more memory, like from 128 megabytes up to 3 gigabytes, it's not just memory, it's not just RAM. You might say, I don't need RAM. My workload only needs CPU. Why do I need to add more RAM? Well, it's power. Think of it as power. If you give it more power, it will run faster as well, simply put. Just to give you an example, imagine a very useful workload that is computing all the prime numbers up to 1,000,000 times. Super useful. A lot of people do that. If I give it 128 megabytes, it will run for about 11 seconds. And that's how much I'm going to spend, around 2.4 cents of a dollar. You might say it's expensive or not. That's subjective. Now, if I start giving it more power, yes, I will spend slightly more, but it will run twice as fast. Is it worth it? Up to you. The great thing, and this is from 2017 when I started thinking about this kind of numbers, if I start adding more and more power, for example, up to 1 gigabyte, as you can see, I'm running 10 times faster, and I'm spending basically the same, 2 plus minus $0.00001. So that's basically the same number. And is it worth it? Yes, in my opinion, it's running 10 times faster. I'm spending the same. Why does it happen? Because you are paying per 100 millisecond execution intervals. So if you can run faster, you might spend the same. That's completely a different way of thinking about cost for serverless functions. Now, let me show you the same in a graph, because we are primates. We can understand charts better than numbers. So that's what happens. In the x-axis, you have power. From left to right, it's increasing power. The red line is always execution time. As you can see, it's going down from up to 36 seconds down to about 2.5 seconds. Okay? Time goes down. That's good. Performance improvements. The blue line is cost. And what I was expecting when I started working on this stuff was that if I increase performance, cost must go up, right? Wouldn't you expect the same? In reality, you can make it cheaper while you are going faster. Now, this never, ever happens in the IT industry, so that's why I'm excited about serverless. If I give it more power, as you can see, the average execution will be up to 5, 6, 10, depending on the workload, times faster, and maybe 10, 20, 30% cheaper. Now, this is a very CPU-bound example, and later I want to show you our other kind of situations and patterns where this may or may not hold. For CPU-bound workloads, this is very true. I want to give you another example of cost-aware performance optimization. Imagine you have two functions, A and B. And function A is running on average for 310 milliseconds. So we are paying for 400 because that's the next interval. Function B is running for, on average, 480. So we're paying for 500. Now let's imagine we have a team of n developers, not n small enough. It's never infinite. And we have to decide which functions to optimize. There are a million ways to look at it. Let's simplify the problem and say that after a very quick analysis, we show that we can probably optimize 5% of the cost, of the execution time for function A and 15% of the execution time for function B. Now, who would go and optimize function B? Raise your hand. Not too many, but a few. Who would optimize function A? Okay, not as many either. If you are undecided, it's normal. Don't worry. It's not so clear anyway. But if you do the math, and we do some, it's still an estimation, but if you do some math, if we cut 5% of those milliseconds, we go below the 300 threshold, so we are now paying 25% less on average, right? If we do the same here, it doesn't happen, because we are still in that 400 to 500 millisecond range. So we're not cost optimizing anything. Well, you might say those 72 millisecond optimization is great if it's a latency-sensitive, customer-facing application. But if it's not, why should you work on that function at all? You're not saving any money at the end of the week after you spend 32 hours of development cutting 72 milliseconds. So I want to give you this idea of cost and performance are related. If you want to decide what to optimize, you have to look at these things, visualize it, and decide when to do it and what. Now, I work on this idea since 2017. I was still a customer of AWS. I didn't work for AWS. But I came up with a tool to visualize these things and to basically adopt a data-driven approach to solving this kind of problem. So I called it AWS Lambda Power Tuning, because I thought this was a tuning process. There is no magic. There is no magic guess that you can take. You actually have to go and try to run it and see which one works better. And the great thing of serverless is you don't have to spin up a huge cluster just to run these tests. You can just do it, run some invocations, and get some numbers out. So what this tool is doing, it's powered by step functions that gives you this kind of visual orchestration. And you provide your function as input. So the initializer will take care of setting up the function. The executor will actually run your function in all the power configurations that you decide. And then it will crunch some numbers and tell you, hey, the optimal power memory configuration for your function is this. Go and use it. It's open source, so it's not a product. It's not a service. It's not paid. I'm just it's in the open source. I'm just contributing. There are now a few community contributions too. I don't know if you care about GitHub stars. I kind of like to say up and to the right. So it's getting a bit more popular, version after version. How can you use it? So some JSON. We are all developers, I hope. So you can provide as input a JSON where you specify which function you want to optimize, how many times you want to actually run each power configuration, which power configuration do you actually want to test. It could be 1, 2, 3, 10. There are today 46 different power configurations you can possibly choose. And then you specify the payload, and there are a few more options, for example, to decide if you want to optimize for cost or for performance, for example, 2 different optimization strategies, or if you want to run all the power configuration. There are a few other options well documented on the GitHub page. What do you get as output? This could be as well a black box for you. You don't have to really understand what's inside it. If you're curious, go and check the code. The output you get is some result, and you get the optimal power. In this case, it was 128 megabytes of memory, the average cost corresponding to that power, and the average duration corresponding to that power. You also get some metadata about the state machine itself. For example, you get the cost of execution for step functions and the cost of execution for Lambda, because you are running a cloud service, so it's not free, but it's pay as you go. So I can inspect and look how many invocations the tool performed, and it's always below 1 cent of a dollar. So I kind of think of it as a free tool for what I'm concerned. You don't have to run it at scale. You can run it a couple hundred executions once a month. It's basically free. The other thing you get is a visualization URL. So you can actually go and visualize what I just showed you. So the tool will help you build a visualization of how is the cost going, how is the performance going when you change power. And you are in control, and this is basically a static website with client-side rendering. So there is no data sharing, there's no GDPR mess or anything. It's not even shared with the server, there is no server. It's serverless. Let me show you some interesting examples of different use cases. So far, I showed you the nice CPU-bound example, but let's look at other patterns and cases. First of all, the most common one, in my opinion, is I call it the no-op case. This is a case where your function is not really doing much. It's not doing API calls, SDK calls. It's not doing long-running CPU-intensive tasks or anything. It's just manipulating some data, returning. Okay, not much. Usually, these functions are below 100 millisecond execution. So you can't possibly make it cheaper because it's already below the 100 milliseconds threshold. So as we expect, the execution, the blue line always goes up if we give it more power. What is not really expected, what wasn't expected when I started doing this, is that the performance actually changes, even with these very small, like 5, 6, 10 millisecond execution functions. So you might say, well, do I really care about 5 milliseconds versus 1.5 millisecond execution time? Well, if this is part of a microservice architecture and you want to shave off 5 milliseconds here, 10 milliseconds there, and ultimately the customer will see 25 milliseconds improvement, well, it might be worth it. So for example, if you choose the cost optimization strategy, it will tell you always 128. If you choose the speed optimization strategy, it might tell you, yeah, 3 gigabytes, it's always the fastest in theory. But there is also a hybrid, a weighted optimization strategy where you can say, give me a weighted kind of a trade-off between speed and performance, and in this case, it might just actually tell you 256, because that's where you get the sweet spot. Now, let's look at another CPU-bound example. Here, I'm using numpy for doing matrix multiplication and invert, like data science kind of stuff. As we expect, the execution time is going down quickly, so more power, it goes faster, up to 7 or 8 times faster. What's surprising, and what was super interesting for me to visualize when I started working on this, is that the cost line is almost flat. So I can be 20, 30 times faster with a flat cost. So don't always assume 128 megabytes is the cheapest option, or the fastest options, almost never. So deciding where to put your configuration here is basically up to you. How much performance are you ready to get for an increasing price? Can you pay 10% more for 100% performance improvement? Up to you. This is the same prime numbers example. Here I'm computing prime numbers, so very CPU bound. What is surprising in some of these CPU bound examples is that the price is actually going down. So my opinion is there's absolutely no reason for not giving more power to this kind of workloads, because you can be faster and cheaper. If you find a reason to not give it more power, come to me. I want to know why, because I can't find it. What's happening here below the 1.5 gigabytes is that you get multiple threads. So my algorithm was not actually leveraging more than one thread. So at some point it becomes more expensive. But if I was able to use 2 or 3 threads, I might actually be able to go down, even at 3 gigabytes. What happens is that you look at here and say, hey, 1.5 gigabytes is the optimal value. But is it? Can you go deeper and be more granular and check some values in that interval? And what you actually find, here I tested them all, is that around 1.8 gigabytes is the optimal value. So what I suggest is, okay, find a local optimum value and then try to go deeper in that interval and see if there are absolute optimal values overall. Another network-bound example, here I'm calling a third-party API. Third-party API means out of AWS. And as you can imagine, I have absolutely no influence over their performance. My function, unless it's actually downloading a lot of data, the execution time is basically flat. I don't influence. My power doesn't influence their power, right? Even if they are serverless. So here, it's really up to you. You might get slight performance improvement based on the network, but usually here you want to go 128 megabytes because it's actually the cheapest all the time. Network bound, for AWS APIs, this is slightly different because it's internal network. So there is a slightly different network response, let's say. So what's happening here, I'm doing 3 DynamoDB queries, and as you can see, the cost line is basically flat as long as I can take off some milliseconds, and I go from 300 to 200 to 100 milliseconds, and then I can make it cheaper. So what you want to do is find a sweet spot. In this case, it's probably here around half a gigabyte. Also note, there is no correlation whatsoever between the two curves. So the fact that they are also meeting each other there is absolutely coincidental, but sometimes it helps to visualize it. Another network-bound example. Here I'm downloading a lot of stuff. This is not a typical use case for Lambda. You don't want to do that. You're probably paying for a lot of network idle. But if that's what you need to do, you can really make it cheaper. My suggestion for specifically S3 download use cases is enable multithreading. If I show you this, you will say, yes, 128 or 212 is always optimal. If you change one line of code and you enable multithreading, it completely changes. Because now, especially around 2 or 3 gigabytes, you have 2 threads. And so you can actually download much faster. And if you shave seconds, you might be cheaper. So a slightly different pattern. Now, I didn't want you to memorize or anything. What is my message here is that there are these cost performance patterns. And the more I look at them, the more it's easier for me to look at your code and know what kind of visual patterns to expect. Or vice versa, I can look at a pattern and already see what your code is doing. Is it network? Is it CPU? Is it memory bound? So my call to action for you is play with the tool, try to visualize some numbers. It's much, much easier to understand than looking at logs or looking at a table full of numbers. And try to think in terms of patterns so that you know when it makes sense to optimize and to give it more power. CPU bound, network bound, and so on. A few takeaways. We have seen some best practices. Try to understand what you're trying to optimize. Is it the cold start? Probably you want to just go with provision concurrency. It solves a lot of problems. Let's call it power. I don't know. We decided to call it memory, but I think it's more meaningful as a word. You might actually even use the tool as part of your continuous integration, continuous delivery. Why not running power tuning every time you change the code, tune it for power, and just deploy the optimal value? Think in terms of categories, workload categories, and cost performance pattern. That will help you have a mental framework to think about numbers, cost, performance, and so on. And then, if you really need help, the tool is free and open source. Maybe you want to contribute as well on GitHub. Go and build something. Let us know what you are building. We are at the booth here in the other room. Thank you all. I think now we have lunch, so enjoy.